the red around it. The other pieces, the front end processes, the screenings, and where you get the grid out, and the clarifiers and the filters and the disinfection are all designed at peak flow. So peak flow makes a big difference in the size of a plant. And if you can do something with that peak flow, you can reduce the size of some of those components. So one of the concepts we looked at is that you have existing lagoons out there, and they are a value. They're an asset the municipality has. And what the lagoons can be used for is they can damp out those peak flows. So they actually act as kind of a buffer storage. So during the summer months when the flows are high, you can sort of pump out of those lagoons kind of an average lower rate, and let the lagoons sort of fill up during the summer and draw down during the other portions of the year, which then makes all these little components a lot smaller, at least the ones that were on the front and back end of the plant. And just to see what the impact of that was, is that this is the current design that the red is kind of, that table is the current Dillon design, the current design that was tendered. And it shows peaking factors of the screens is 13.5, the secondary clarifiers and the back end at 5.7. A typical peaking factor for a municipal sewage treatment plant is about 3.3 to 3.4 on the average day flow. Now, what they did to get to the 5.7 is they said, okay, the maximum month is the summer, so we're going to actually kind of assume the summer is our average day flow, and we're going to peak that. So that's 1.7 times higher. And we take 1.7 times 3.4. If the math works out, it comes out to about 5.7, or in about that ballpark. So you can see by that little bar graph that there's quite a difference between using equalization. The blue bars are equalization, and the red is without equalization, the current design. So you can see that we can make things a lot smaller if we take advantage of one of those 4 lagoons for equalization. Now again, we also took a look at the flows and took a look at the actual design loading flows for the plant. The current plant that was tendered had a design capacity of about 4,600 cubic meters a day. We took a look at what the 20-year design flows would actually be using existing flows plus the current flows that are committed plus growth for 20 years. For Lambton Shores, that came up to 1,600 cubic meters a day. South Huron came up to 873 cubic meters a day. And you also know that the blue water is not part of at least the initial phase of the plant. So that came out to a flow of 2,473 cubic meters a day versus the 4,659 cubic meters a day that the current plant was tendered on. So we're almost looking at not quite half as small, but almost half the size of the plant. And this is just some of the peaking flows or peaks that have been measured at the PS2, and it's really just more of a relative thing. The one thing this doesn't show is the effect of the binary. But what this does show is if you take a look at the sort of the springtime flows or the flows in around the wintertime, December, January, are in the average daily flow is a little less, it's about 7 liters per second. When you look at the peak hour flow on the Canada Day weekend, it's about 21 liters a second.
Just if I may, you mentioned the peaking factor of 3 when you presented it to the board, and you were going to look at the pinery flow.
Yeah.
July 1st weekend that the pinery would have been.
Yeah, and I'll get to that. I didn't modify this slide, but yeah, what that does is the flows coming into the PS2 have a peaking factor of about 3. The pinery flows, we're still talking to the pinery to find out what their pump sizes are, but work that sort of Gamsby Manero had done sort of suggests that once you add pinery in, you're looking at a peak of about 4 rather than the 3 that's shown by this graph. But I just sort of bring that up to say it's not 5.7, it's a little bit lower, and that gives us sort of confidence, sort of our current thinking is we're kind of on the right track. But again, as Mayor Weber's pointed out correctly, once the Pioneer is not in that, once you add it in, it does push the peak up to about around the 4. So just to go back, and what I think I'm repeating myself, but the tender design was 4659 cubic meters a day. The 20-year flows that we're looking at now are 2473, and actually because they designed for the peak month, which is the July-August period, they actually designed it for 7867 cubic meters a day. Now one of our options is to use equalization, which then brings our design back to the 2473. So you can see we've really sort of taken this plant and made it a lot smaller to try and reduce some of the costs. Once we sort of looked at the flows, got kind of our basic design criteria, we then said, okay, what's our evaluation criteria? We came up with a fairly substantial list of evaluation criteria, and I won't go through each of those, but it does sort of talk some of the soft factors as well as some of the cost factors and operating factors. Wanted to make sure that it was phased. It could be built in phases so that, if blue water comes on, or if if you see growth greater than what's projected for the 20-year, then again you can add a module and you can phase the plant up. We also wanted to look at the impacts on the environmental study report, because that's fairly important, and also on the grants too. So we took a look at all those factors, and then we also took a look at, once we had our evaluation factors, we came up and said, okay, what are our options that will fit the criteria that the mandate the group had. And what we came up with was existing plant as tender, which is really the base. It's our base. You know what that price is. We also had the half orbital as tender, which was the phase 1 of the tender price. The option 1 is phase 1 and 2. And then we had the orbital, but we used equalization. And we also used the thing that I call value engineering, where we sort of took a look at the plant as designed and said, okay, what's in here that we could eliminate without changing the basic function of the plant. So we did that. We also took a look at the half orbital and said, okay, well, if we can do value engineering on a smaller plant, we can also do value engineering on that half plant. We looked at a hybrid lagoon. We looked at an aerated lagoon with some what we call a SAG, or submerged attached growth reactor on the back end, and some tertiary filter. So we looked at an aerated lagoon that would give us the same effluent criteria performance as a mechanical plant. We also looked at an intermittent sanitation plant and you have to put a future mechanical plant in. We also looked at the existing lagoons and could we just put tertiary filters on them. And the reason those 7 and 8 are grayed out is they don't really meet the criteria. They won't meet that future effluent criteria that the Ministry of the Environment requires. So we looked at them, but once we sort of shortlisted 1 to 6, and kind of 7 and 8 kind of dropped off the table because they don't meet the criteria. And I just threw these up just to kind of show what the options were. So this is existing orbital as tender, which is basically you've grit screenings here for rags and stuff. You've got grit removal here, 2 orbital aeration tanks, 4 clarifiers, some tertiary filters, UV disinfection, the sludge wetland. The half orbital is exactly what it says. It's half of that, although the buildings were built big enough that you could plunk a lot of that stuff already, in the building by just putting in the equipment. The structural concrete and the building roof and all that kind of stuff were there. The orbital with flow equalization kind of resembles that, except everything's a lot smaller. We did take off a clarifier because you still have your redundancy here. And then again, number 4 is really the same as number 2, except we've done some